This conference will now be recorded.
Hello everyone. So today first I will make one correction, that is the last slide of previous class. There I have mentioned this graph, but there is a mistake. Okay, so this graph that I mentioned here, this will be actually rate versus concentration graph. So this is not time, it will be concentration, that is concentration of the starting material, because we know that expression for rate equal to rate constant, then concentration of starting material, and there may be any power, and here we are talking about first order, so it is 1. So here, as we are increasing the value of A, that is concentration, rate will also increase accordingly. Okay, and this is a type of equation like y equal to mx, so it will pass through origin, there is no intercept. In today's class we will mainly discuss parallel type of reaction, but before that we will see the summary of all the types of reactions that we have seen until now, that is zero order reaction, first order, second order, and also the general nth order reaction. Fine. Here we will see rate law, then integrated rate law, what is the unit of rate constant, and from which y and x value, when we will draw a plot, then what will be the y and x axis value for linear plot, that is also mentioned here, and the expression for half-life. When it is zero order reaction, then rate of disappearance of starting material, so it is dA dt, and there is a negative sign because it is starting material. This value is constant, and if it is for first order, then it will be K into concentration of A. So in case of zero order, rate is actually not dependent on the concentration of starting material, that is why it is simply the constant, there is no other term mentioned. And after integration, the integrated rate law becomes like this. You can also write it in this way, that is A naught minus A equal to KT. And for first order reaction, it will be A naught, then e to the power minus KT. Unit for rate constant, for zero order, it is molarity divided by S. That means it is actually concentration time inverse. Here it is mentioned second, but it is not necessary, it may be minute or hour also. And in case of first order, it is simply 1 by S, that means 1 by time, or you can say time inverse. And if we want to get linear plot, then for zero order reaction, in y-axis we have to take concentration of A, and in x-axis it should be time. So as time increases, then concentration of A, that will actually decrease, but it will be linear plot. Okay, and for first order reaction, we have to draw ln A versus T, then only we can get linear plot, because if you consider this expression e to the power minus kt, here actually if we directly draw from here, it will be exponential in nature, but after taking ln both sides, this exponential term will not be present, now it will be straight line. And the expression for half-life, T half for zero order reaction, initial concentration divided by 2k, that is 2 into rate constant, but in case of first order, it is not dependent on the starting material concentration, it is simply ln2, that is 0.693 divided by rate constant. So this is very special about first order reaction, where you will see that half-life is not dependent on the starting material concentration. Next we have second order and nth order. So for second order, here we have seen for first order it is 1, now it will be 2. And the integrated rate law, now it is 1 by concentration of A at time t, you can also write it here as AT, then 1 by A naught plus KT, and here unit for rate constant will be 1 by molarity and second, that means it is 1 by concentration into time. And if we want to get linear plot, we have to draw 1 by concentration A versus T, because if you compare this equation with y equal to c plus mx, here x is t, y is 1 by 80, this total term will be there in y-axis. Then only we can get linear plot, otherwise we will not get it. And intercept value is 1 by concentration of A, that is initial concentration, A naught. Fine. And here T half is 1 by K A naught. Here also it is dependent on the concentration of A naught, and here the relationship is inverse. That is, when you will increase the initial concentration, T half will decrease. But in case of zero order reaction, it is directly proportional, and in case of first order, it is not proportional at all. Now, what about nth order? When it is nth order, here power of starting material, it will be n, and the integrated rate law, it will be like this. But remember, this is not for first order reaction. So first order reaction is the exception, but that is, if we put n equal to 1, that means it is first order. It will be a to the power 0 basically. So you will never get this expression because there is exponential. But if you consider zero order and second order, there is no exponential term. So that is why you can get the second order expression or zero order expression when you put in place of n 0 or 2. But if you put n value equal to 1, then you will not get this first order integrated rate law because here exponential term is present. So except first order, you can put any value, that is n equal to 0, 2, 3, etc., but not 1. Here unit for rate constant 1 divided by m to the power n minus 1. Here see, if you put 1 equal to 1, that means 1 by m to the power 0 into s. So it will simply be converted to 1 by s. And see, for first order reaction also, the unit of rate constant is 1 by second. So here you can get, that is this general expression, it will be applicable for 0 first second. And then if we want to get linear plot, we have to draw 1 divided by a to the power n minus 1 in y-axis, t in x-axis. But here again, it is not for first order. And this general expression for t half, remember this is not for first order again. This is the expression 2 to the power n minus 1, then minus 1 divided by n minus 1 into rate constant, then initial concentration to the power n minus 1. Now, if you follow this expression very carefully, you will see this part is basically totally constant. Fine. That means T half is proportional to initial concentration to the power n minus 1. I mean to say inversely proportional. Okay. So just remember at least this expression, because to solve numerical, you may require this formula. Okay. And this total term, it is actually constant. So that is why T half is inversely proportional to the initial concentration to the power n minus 1. Okay. Next slide. Here we have a problem. And this problem is also related to, that is, we have to find out time. Okay, because see, all these are having unit time. Here we have equation C7H40. So this is basically hydrocarbon. When we are heating it, it is converted to C2H6 and also another hydrocarbon C3H6. Now the starting material here is heptene, 7 carbon, and there will be a double bond, that is why heptene. Rate constant for this decomposition 10 to the power minus 4 second inverse. Now see, from the unit directly you can understand that this is a first order reaction, right? Next, in what time molar ratio of heptene to ethene. What is ethene? Ethene is C2H4. So this is actually ethene. One of the product is ethene, another product is C3H6, but nothing is mentioned about that product. We only have to find the time in which molar ratio of starting material, that is C7H14 divided by C2H6. This molar ratio in the reaction mixture will attain the value 1. Here some informations are also given, that is log 2 value and log 3 values are given, and all the options are in minute unit. So this is the reaction that is given in the question. If we consider that initially when time is 0, concentration of heptene, this is heptene, concentration of heptene is A, and obviously the concentration of two products we have here, C2H4 and C3H6, their concentration nothing will be mentioned because it is T equal to 0 initial time. Now when T is equal to T, suppose X moles of C7H14 decomposed. That means remaining amount of C7H14 will be A minus X. And from 1 mole of C7H14 we are getting 2 moles. So that is why when X mole decomposed, obviously 2X moles will be produced. And look at the other product here. It will be only X because from 1 mole of C7H14 you are getting 1 mole of C3H6. Now here we have to find that time where heptene to ethene ratio, that means C7H14 concentration divided by concentration of C2H4, this ratio must be equal to 1. Now at time equal to T, remaining amount of C7H14, that concentration is A minus X, and the concentration of C2H4, that is 2X. So this is the condition that we have to fulfill, that is ratio of concentration of C7H14. This ratio is same, and the concentration of C2H4, this ratio must be 1. Now from this equation you can see that A minus X will be equal to 2X, that means A equal to 3X. So ultimately we are getting the value of X, which is X equal to A by 3. So now we know what is the value of X. Next, for first order reaction, what equation we follow? That is in terms of KT, if we write, it will be equal to 2.303 log initial concentration, that is A, divided by remaining amount, that is A minus X. Now in this expression we can put the value of small x, because small x we know it is equal to A by 3. So A minus X, that will be equal to A minus A by 3. That means what? 2A by 3. So in this equation, now we will put the value of A minus X. And after putting this value, so here in place of A minus X, we have written 2A by 3. So after calculation, you will see that the value of time, that is T, because K value is given, which is 10 to the power minus 4. So K will be in the denominator if you bringing it in the right hand side. Now K value is given in second inverse. So obviously the value of T that you will get, that will be in second order. But look at the options, all these are in minute. We have to convert second to minute, and for that we will divide it by 60, and ultimately it will be 67.6 minutes, which is closely matching with option A. Okay. So in this way we can solve this problem, and here we have taken the help of this first order integrated equation. Okay, that is not just integrated, it is the logarithm version of the first order equation. Kt equal to 2.303 log A by A minus X, because here after putting this value of X, that is 2A by 3, this log term, it will be changed to AA will be cancelled, and ultimately it will be log 3 by 2. Okay, and log 3 by 2 means what? Log 3 by 2 is basically log 3 minus log 2. And look at the question here, these two values are given. So what you will do, the equation ultimately will become 2.303 10 to the power minus 4, and in the bracket it will be log 3, that means 0.4771 minus 0.3010. If we do this calculation, you will get 4055.6 second, and then we have to divide it by 60 so that we can get the value in minute. Fine. And T, there is a chance of mistake that I want to highlight here. 4055.6 second. So if you are not careful about the units, look, you may by mistake choose option B, but it is not 4055 minute, it is 4055 second. So this option, be very careful. Fine. Inversion of cane sugar proceeds with constant half-life of 500 minutes. But remember, condition given at pH 5. So half-life is dependent on pH. pH means negative logarithm of H plus concentration. So ultimately it means what? Half-life is dependent on H plus. So it proceeds with constant half-life of 500 minutes at pH 5 for any concentration of sugar. That means inversion of cane sugar. So cane sugar is the starting material, that is reactant. And it is mentioned here that the half-life is constant. It is not dependent on the concentration of sugar. And it is true for which order of reaction? It is true for first order reaction, because we have seen first order reaction, T half value is equal to ln2 divided by rate constant. That means it is not dependent on starting material concentration. So from this you can understand this is for first order reaction. For any concentration of sugar. However, if you are changing the pH, that is if now the pH is 6, half-life is also changing to 50 minutes. Now for this reaction, rate equation is given, but here the power of sugar and H plus concentration that are not mentioned. M and N, two power are given. M is power of sugar concentration, N is power of H plus concentration. We have to find the value of N, and it is integer type question, so value of N will be whole number. It may be 0, 1, 2, 3 like this. Now T half is equal to 500 minute at pH 5. pH 5 means negative log H plus equal to 5. That means concentration of H plus 10 to the power minus 5. Similarly, T half is equal to 50 minute when pH is 6. That means now H plus concentration 10 to the power minus 6. Now remember the first slide of today's class where we have seen that T half for nth order reaction. Suppose you do not know what is the order of the reaction. So T half is proportional to 1 divided by A to the power n minus 1. Okay. Now here H plus is one of the reactant, right? That is starting material you can consider, because it is here acting as catalyst. So it is also mentioned in the rate expression, that is sugar and H plus both are present. So we can consider here A is basically H plus. So what I am trying to say that T half will be proportional to 1 by H plus concentration to the power n minus 1. Okay. Now we have here two conditions, 1 and 2. So when T half, suppose at pH 5 divided by T half at pH 6. So this should be equal to, now the concentration of H plus we have already mentioned here. So when it is pH 5, the T half and the pH 6, this ratio of T half, it should be equal to 10 to the power minus 6 divided by 10 to the power minus 5 n minus 1. Okay, you can also write n minus 1 individually, but I have written it together. Now T half at pH 5 is 500 and at pH 6 50. So this value is 10, and in the right hand side 10 to the power minus 6, 10 to the power 5. That means it will be 10 to the power minus 1 n minus 1. Now if we are removing this minus sign, it will be 10 to the power 1 minus n. Now compare both sides. Left hand side we have simply 10, right hand side we have 10 to the power 1 minus n. If you compare both sides, basically there is a power 1. So we can say from this 1 equal to 1 minus n, that means the value of n is 0. So in the rate expression, this is actually 0. That is, with respect to H plus, here order will be 0. So the value of n is 0. Fine. Now don't be confused between the half-life and rate. In the rate it is mentioned that sugar having power m, H plus having power n, and we have just calculated that n is 0. That means rate is not dependent on H plus concentration, but as it is first order reaction, obviously the value of m will be 1. So it is dependent on sugar concentration. But when you are talking about half-life, as it is a first order reaction, it will not be dependent on the starting material concentration. But that doesn't mean that it will not be dependent on H plus concentration. When you are considering rate expression, then it is dependent on sugar concentration but not H plus. But when you are considering T half, now it is reverse. It is dependent on H plus concentration but not on the concentration of starting material, that is sugar. That is, it is mentioned for any concentration of sugar. Okay. Another integer type question. A drop of solution of volume 0.05 ml. It is a drop, so very small volume, right? 3 into 10 to the power minus 6 moles of H plus ions are present. This is the number of moles of proton, H plus. Rate constant for the disappearance of H plus given 10 to the power 7 moles per liter per second. How many nanoseconds it required for H plus ions present in the drop to disappear? So see here, how many number of moles of H plus present in 0.05 ml, that is mentioned, but it is not mentioned what is the initial concentration, what is the final concentration. But still it is asking how many nanosecond it will require for the H plus ions present in the drop to disappear. That means this number of moles that is present, if you find the corresponding concentration, because this number of moles present in this volume. So what is the number of moles that is present in 1 liter, that is 1000 ml? If we know that, that means we now know the concentration. So basically this amount of H plus to disappear, what should be the time required? And as the time will be very small because it is a single drop, so obviously the number of H plus ions, it will be very low. So that is, it is asking in nanosecond. That is a very, very small unit of time. So first we will find out what is the number of moles of H plus present in 1 liter. 0.05 ml contains 3 into 10 to the power minus 6 moles H plus. So if it is 1000 ml, that means 1 liter, divided by 0.05 into 1000. Now here it is 1000 means 10 to the power 3. So it will be 3 into 10 to the power minus 3. Then 0.05 means what? 5 divided by 100. So now we will write it in this way. 10 to the power 2 and 10 to the power minus 3. So it will be 3 by 5, 1 by 10, 3 by 5. So this is the number of moles of H plus that is present in 1000 ml. So we can say this is actually the molarity. Now for zero order reaction, the expression that we follow, initial concentration minus concentration at time t equal to kT. Here individual value of A naught and AT not given, but its difference you can consider as if this is 3 by 50, that is the concentration of H plus, and value of K is 10 to the power 7 moles per liter per second. So the value of T that you will get, that will be in second. Now we will put 3 by 50, 10 to the power 7 into T. So T will be equal to 3 by 50, 10 to the power minus 7. And if you do the calculation, it will be but what we'll do, nanosecond means what? 10 to the power minus 9 second. So we will write it here minus 9. That means this will be converted to 6. So this is the value of time in second, but we have to express it in nanosecond because it is integer. So nanosecond 10 to the power minus 9, that is 1 nanosecond. That means it is equal to 6 nanosecond. So answer is 6. Fine. Again, integer type of question. Rate expression for a reaction given as minus dA dt equal to alpha into concentration of A divided by 1 plus beta into concentration of A. Now alpha and beta, what is this? It is constant. And it is also mentioned greater than 0. That means these two values are positive. If the initial concentration of A, that is A naught, is quite low, under that condition, what the half-life period of the reaction in seconds in nearest possible integers? Value of alpha given, but not for beta. So remember, we have to find half-life period in second under this condition. This is very important here. That is A naught is quite low. That means actually that you can ignore the value of A naught because it is quite low. But before that, how we will start? We will write the expression. That is the expression that is given here, and then we will do both side integration. So this is the relation that is given in the question. Next, what we are doing? Bring dt in the right hand side and all the portions in the left hand side. In the denominator, we have 1 plus beta A. Now it will be in the numerator, and alpha A, that will be in the denominator. Now if we are doing, that is if we are separating these two parts, that is 1 by alpha A into dA, this is the first term, then beta by alpha into dA. Now we will do integration. Alpha is constant, so it will not be included in integration. Beta, alpha, these will also be outside of integration. And here limits will be, see, initial concentration is A naught, so A naught to AT. This is also A naught to AT. And here it is 0 to T. because when it is time 0, concentration of starting material A is A naught. When it is time t, concentration of starting material A is AT. Now, after integration, according to the formula, when there is dA divided by A, then we get ln. And it is simply dA, so it will be AT minus A naught. For simplicity, you can also remove this AT. So here it is simply written A. And right hand side, it is also only T, negative sign was already there. Now, if we are removing this negative sign, left hand side, this ratio will be interchanged. Now it is A naught by A. And see, now A is here, A naught is here. That means negative sign we have taken both sides. So until now, we have, that is after integration over this expression which is given in the question, we are getting this type of expression. Now remember, here A naught is quite low. That the condition we have to keep in mind. And we have to find half-life period. Now half-life period means the time at which concentration becomes half, that is 50% will be consumed. So when T is equal to T half, basically this ln A naught by A, what we can write? Now in place of A, you can write A naught by 2. So if you put A naught by 2 here, it will be converted to ln 2 plus beta by alpha, then A naught minus A naught by 2. Okay. Now A naught minus A naught by 2, it will be also A naught by 2. So ultimately what we are getting, ln 2 value is 0.693 divided by alpha plus beta into A naught divided by 2 alpha equal to T. Now this expression, that is we have to use this expression to ultimately write T half. So when it is T half, basically the equation will change to this form. So 0.693 divided by alpha and beta A naught divided by 2 alpha, that is the same expression. Now A naught is tending to 0, that means now we can put the limit that A naught is tending to 0. It tends to 0, that means it is very low value. So that is why this second expression, now it will be negligible. You will be left only with this expression. And alpha is given, beta is not required because this is already cancelled. Now put the value of alpha, 0.693, it will be that is 10 to the power minus 3 in the denominator. Now it will be 10 to the power 3. So ultimately it will be 693 second. So this is the half-life period for the reaction in second in nearest possible integers. And this value it is in second because alpha it is already given, it is second. Fine. So this is integer type. The value is a whole number, 693. So at a first glance it seems very difficult, but actually it is not. And remember this condition here, that is very important. We have to keep it in mind. So we have discussed many problems which is related to rate expression, order, etc., etc. Now we are discussing a completely different topic, which is parallel reaction. So this type of reaction example we have not discussed before. From the name you can understand that two paths in the reaction will be going on simultaneously. Here we have starting material A. It is producing B with the rate constant K1, and simultaneously it is also producing C with the rate constant K2. So the reactions in which one or more reactants, here we have for simplicity only one reactant, but that is not necessary, it may be more than one. So one or more reactants react simultaneously in two, that is minimum two, because if there is not minimum two pathway, no question of parallel reaction. So minimum two or more pathways, it may be three also. Suppose there is another, you are getting D, this is K3, and it may go on. Okay, To give two or more products, these type of reactions are known as parallel reaction. And see, there is another term which is also possible for this type of reaction is side reaction. Now side reaction, probably you have heard this term, because remember in organic reactions it is very frequent, we have seen that you are getting the major product and there is a side product which is not desired, which is minor. Okay, so this is also one type of parallel reaction example, right? Because both the path, though they are not dependent on each other, but both are going on simultaneously. Okay, and among these two products, here we have B and C. One of them may be major, but it may be 50-50 also. That depends on what type of reaction you have taken. Now look at this plot. We have taken concentration of A in the, not just concentration of A, concentration of product also B and C in the y-axis and time in the x-axis. So with time, gradually the concentration of A, it will decrease, and the concentration of B and C both are increasing with time. But see here, the line of B, it is above the line of C. That means any particular time if you consider and if you draw a line, it is cutting at these 2 points. Now if we extend this line, the concentration of B, it is higher than the concentration of C. So we can say that here B is major product because its concentration of high. Suppose it is 70%. I'm just saying arbitrarily it is 30%. So it will be having more concentration. So we will say that B is major product, not C. C is minor product. Now look at these examples. These are from organic chemistry. CH3CH2Br in presence of base. Here we are getting substitution product, that is Br is replaced by OH, and we are also getting elimination product where HBr is removed. So this is substitution reaction, this is elimination reaction, but both are going on. So it is also example of parallel reaction. Second example, we have taken phenol in presence of nitric acid. Two types of product. In one type we are getting orthonitrophenol, another one we are getting paranitrophenol. So this is also example of parallel reactions. The overall reaction rate, because why we are saying overall reaction rate, because you have two individual mechanism through individual path. So there will be individual rate constant, and also overall rate and overall rate constant. Okay, so now we have a new term which is overall, that is a combined effect. Okay, now for individual path it is K1 K2. So when it is dA dt, it will be minus K1A. Why minus sign? Because A is starting material, with time it will decrease. Now K1A, this is for the first mechanism, K2A, this is for the second mechanism, and if you take common, fine. Now suppose the overall rate constant is K. So in that case the equation you can write in this way, that is overall rate constant. Okay, but overall reaction rate, that can be expressed in this way. Now from this expression, that is dA dt equal to minus K1 plus K2 into A, if we do integration, so detailed integration process I have not mentioned it, and that is not required. You just have to remember this final expression. So concentration of A at any time t is not written for simplicity, that is equal to initial concentration, then exponential to the power minus K1 plus K2 into T. Now you can also write the same equation in this way, that is minus Kt, because K is equal to K1 plus K2. So for parallel reaction, individual rate constant, if you just add them, you will get the overall rate constant. So what expression we have obtained? A equal to A naught e to the power minus Kt, where K is K1 plus K2. So you can understand this expression, it is just like the first order expression. Only difference, now we have two rate constant. Right? So this is the concentration of starting material at time t. But you can also find out the concentration of products. Products means B and C. These two are the products. So what will be the concentration of product at a particular time t? That also we can find. dV/dt. So just like dA dt we have done in the previous slide, now it is dV/dt. So when it is dV/dt, we have to consider only the rate constant K1 because B has nothing to do with K2. That is only for C, not for B. So that is why we have written only K1 into A, and there is no negative sign because B is product. Now we know the value of concentration of A. Remember, this is the value of concentration of A. So that is why we can write it. So dB/dt will be equal to this expression, and if we do the integration with respect to time, ultimately we will get the concentration of B, this type of expression, and we will also have a constant here. You can also write this expression in simpler way, that is in place of K1 plus K2 I am writing K e to the power minus Kt. Okay, this is another way you can express. Now this value of this constant that we have obtained after integration, you can find the value of this C1, and how that is possible. Suppose at t equal to 0, that means when time is 0, then obviously the concentration of product B is 0 because initially only A is present. So put B equal to 0 here and t equal to 0 here. So when t is 0, e to the power 0, it will be 1, and ultimately the value of C1 will be this. Because there is a negative sign, this part will be 1, left hand side it is 0. So you are getting the value of C1. Now put this value of C1 in this equation, and ultimately the concentration of B, you will get this type of expression. Again I am simplifying it by writing it in this way. A naught 1 minus e to the power minus Kt. You can also write it in another way. I am writing all of this. That is all the possible expression. It is A naught, that is if you bring A naught inside the bracket, now it will be changed to A naught minus A. So these are the different ways by which you can express the concentration of B after time t. Similarly, we can also find the value for C because that is another product from the second mechanism. And just like the expression for B, this is also same. But now it is K2. That is the only difference. 1 minus e to the power minus Kt, or we can also write K2 by K, concentration of A naught minus A. Because remember, A naught into e to the power minus Kt is basically concentration of A at any time t. So this is equation 2, this is equation 1. Now if we take the ratio of B by C, that is in the right hand side you are taking this ratio divided by this one. Now all these terms are same, only you will be left with K1 by K2. So this relationship is very important because here one conclusion we can draw, that irrespective of how much time is elapsed, this ratio of concentration of B by C, that is from the start, that is from initial point, where that is we have assumed that initially at equal to 0 there is no B and C. Under this condition, the ratio of concentration of B by C, it is equal to K1 by K2. That means it is a constant and it is not dependent on time. So suppose this ratio you are taking after time 10 minutes, then you are getting the value K1 by K2. Then again you are doing the same calculation, but now it is after 20 minutes. But still these two values are always same. That means the ratio of B by C, irrespective of time, it will always be same. So this is actually constant. So remember this relationship for parallel reaction, that concentration of B by C, where B is product of one path, C is product of another path, that should be equal to their rate constant. So K1 is the rate constant for the formation of B, K2 is the rate constant for the formation of C. Fine. Now we will see the relationship overall rate constant. Now until now we have not talked about anything about the overall rate constant and overall activation energy. We have just seen the individual expressions. So when it is overall, what will be the expressions? Remember this equation, this is Arrhenius equation, that is the relationship between rate constant and activation energy EA. Okay, this expression we have already seen. Now take ln both sides. So when you are taking ln both sides, it will be changed to this type of equation. Okay, and if we are doing ddt both sides, then ln a, as it is a constant, it will be 0, and ea by r, this part is also constant, so this will be same. And remember ddt of 1 by t is basically minus 1 by t square. So that is the reason this minus minus cancelled. Ultimately we are having the term ea by rt square. So if that is the case, now ea will be equal to, just bring rt square in this side, rt square into ddt of ln k. This is the expression for activation energy. Next, what we will do, this is the overall rate constant, that is equal to summation of these two. Now for individual rate constant, that is k1 and k2, you can write the corresponding Arrhenius equation. So what is the difference here? Activation energy is E1 for k1, activation energy E2 for k2, and these exponential terms that are also different. Now in place of k, you can write this expression, right? So okay, before that what we'll do, just remember this one. Suppose this is equation 1. So if you put the value of k, so this is the value of k, so you have to put this value in this equation 1. Remember ddt of ln k. Okay, so see, that is why rt square then ddt, and this is the total expression for k. Now if you are interested, you can go to the details, but we are interested in the ultimate relationship, not in the derivation. EA will be equal to this expression. So see, overall activation energy, how it is related to individual activation energy and rate constant, this relationship now we can see here. You can also write it in this way, U1 K1 E2 K2 divided by K. So overall activation energy, in this way it is related to individual activation energy, that is E1 E2, and also individual rate constant K1 K2. So this is also another important relationship. Consider the parallel first order reactions that is given here. From A we are getting B, corresponding T half mentioned here also. From A we are getting C, corresponding T half mentioned. Now what we have to find out, the half-life for the decay of A. Okay, so half-life for the decay, that is overall half-life we have to find in hours. So this is the unit, and any of these values will be correct. Now for parallel first order reaction, this relationship we have already used. So if that is the case, just keep it here in this way. Now we know that as it is mentioned, it is first order. For first order, T half is equal to ln2 by k. Now in place of k, we will write k1 plus k2. Okay. Now k1 is equal to, that is just focus on individual path. So for k1, it should be equal to ln2 divided by T half for path 1. Similarly, k2 will be equal to ln2 divided by T half for path 2. So we have written in place of k1, k2 these two expressions. Okay. And ln2, ln2 will be cancelled. So we will be left with this type of expression. Now T half 1, this is actually T half 1. and this is T half 2. So put the value of T half 1 and 2, it is 4 into 2, and in the denominator we have 4 plus 12. So this will be actually 48 by 16. So this is 3 hours. 3 hours means this is option B, which is correct. So taking the help of this relationship, which we have already seen in first order reaction, and we also know here that K is equal to K1 plus K2. So we have taken the help of these two equations to find the answer. This is a multiple correct type. More than one may be correct. Again, we have two parallel path reaction. Rate constant and EA all are given. Overall rate constant K, individual rate constant K1, K2, both are in second inverse. That means it is first order. And activation energy is E1 for B, E2 for C. Now we have to find correct statement. It may be more than one. Arrhenius constant for both the processes may have different values. Now just remember Arrhenius expression, that is K equal to A into e to the power minus KT. Sorry, EA by RT. So Arrhenius constant, this value of A, it may be different. Just see in the previous, not here. In this expression, what we have done, for path 1, the pre-exponential term is A1. For path 2, it is A2. So it may be different. It is not necessary that it has to be same, because it is different path. So when it is different path, pre-exponential factor, it may be different. Arrhenius constant for both the processes may have different values, may have or may not also. So this is true actually. Then overall energy of activation. Remember this expression we have just observed in the previous slide, right? Then, so this is also correct, true. In third one, we have expression that is concentration of B, K1 by K, A naught in the bracket 1 minus e to the power minus KT. So this expression we have seen, remember, this is the expression, that is K1 by K, A naught 1 minus e to the power minus KT. So this expression is also correct. This is also true. And concentration of B by C, remember, irrespective of time, that is whatever is the time, the concentration ratio of B by C, it will always be constant. So it is not dependent on a time. So whether it is after 10 minutes or 20 minutes, the ratio of concentration of B by C, it will always be same. That is, it is always equal to K1 by K2. So the last expression is also same. So here all correct. A follows parallel path first order reaction giving B and C. K1 for the first one reaction, K2 for the second, and C here K2 value is mentioned, but not for K1. Another interesting thing you can observe in this problem, up until now all the parallel path that you have seen the examples, it is simply A, that is no coefficient is there, but here we have some coefficient, that is from 5A, that is 5 moles of A, we are getting 1 mole of B, 2 moles of C. So this coefficient here, it will make some difference. If initial concentration of A is 1 molar, determine millimolar concentration of C after 10 hours of reaction. Some values are given, that is e to the power 0.9, the value is given 2.46, and overall rate constant, that is K1 plus K2, that value is also given in second inverse. So you know what is the overall rate constant value, you also know what is the value of K2, but you do not know what is the value of K1. Give your answer in nearest possible integer, because it is integer type and it should be in millimolar concentration, not molarity, millimolar. Fine. For first order reaction, parallel path, this type of expression we have already seen. So if we use this expression, that is A divided by A naught, this will be equal to e to the power minus k1 plus k2. That means e to the power minus kt. Now if we interchange numerator denominator, this side negative sign will be removed. Now the value of kt is, k value is given 25 into 10 to the power minus 6, and t value, that is 10 hour. But remember, here the rate constant is in second, so time is in, it is given in 10 hour, but you have to convert it to second. So that is why time will be 10 into 3600. So the value of kt that we will get from this is 0.9. That means e to the power 0.9, and this is equal to 2.46. So now we know what is the value of the ratio of A naught by A. Okay. So if this is the case, next, after all, we have to find the concentration of C. Now for concentration of C, if you consider this expression, it will be basically, if we write in simple way, A naught minus A naught e to the power minus kt, isn't it? Now we can also write A naught minus A, because this expression is equal to 80. You can write 80 or not. Okay. So if we want to get the value of C, basically we have to find this difference. And for that, what we will do, A naught minus 80. A value initial concentration mentioned 1. That means 1. And in place of 80, this is actually 80. We can write, see from this equation, 80 is basically A naught by 2.46. Now A naught is 1, so it will be 1 by 2.46. So ultimately it will be 1.46 divided by 2.46. Okay. Now we will use this equation. Suppose equation number 1. So put all the values. C will be equal to K2. K2 value is 5 into 10 to the power minus 6. K value overall 25 10 to the power minus 6. Next, K naught minus 80, that we have just calculated, 1.46, 2.46. But this is not the end of calculation, because here we have to remember, from 5 moles of A you are getting 2 moles of C, right? But here we have taken only 1 mole of C. So the other calculation that we have to do is, from 5 moles of A you are getting 2 moles of C. So from 1A you are getting 2 by 5 of C. Okay. So the in this that is calculation, we will multiply with 2 by 5, because we are trying to get the concentration of C. Okay, after 10 hours. So in this calculation, if we multiply 2 by 5, then only we will get actual value. So it is 5. Ultimately it will be 0.04747. Okay, but remember this is in molarity. Okay, we have to change it to millimolar. So for that we will multiply with 10 to the power minus 3. So it will be converted to 47.47. But possible nearest integer, so that is why the value answer will be 47. Okay. So we will end the session here. Thank you for listening.